Question 8, we have a particle of mass 10 describing a circle on a smooth horizontal table, so we'll have a reaction force. It's connected by a light inelastic string 0.5 to a point which is 0.4 vertically above the center. The reaction force is 20. Okay, diagram here, fixed point P, length of string 0.5 meters, and it is 0.4 vertically above the center, which would leave 0.3 by Pythagoras, this 3, 4, 5 triangle. We have A, so we have cos of A is equal to 0.4 over 0.5, I'll just say 4 over 5. So 4t over 5 is the force going in this direction, putting my t on, and we have sine A is equal to, actually that's the wrong way around, that's my sine A, look at it wrong, just change it, sine A, 4t over 5, that direction, cos A, 0.3 over 5, or 0.3 over 0.5, 3 over 5, so 3t over 5 is my force going in this direction. mg is equal to 10g, 1098 newtons for mg. The reaction at the table is 20 newtons, 20 newtons going in that direction. So we can set up my first equation, 20 plus 40 over 5. That will be equal to the downward force, 98. So 40 over 5 will be equal to 78. So t will be equal to 5 times 78 divided by 4. 5 times 78 divided by 4 is 97.5. Just double check, 97.5 newtons for the tension in the string. Angular velocity, okay, so my 3t over 5 angular velocity, mw squared r, so 3 over 5 times t is 3 over 5 by 97.5, which is, actually, let me see, I think I might get a cancellation going on here, m, which is 10 times w squared times the radius, which is 0.3, yeah, there's my 3, 10 by 0.3 and 3, so I get the left hand side 19.5, 0.5 less than 20 will be w squared, so w will be equal to the square root of that, which is 4.41, one decimal place. The angular velocity is 4.4. So angular speed is increased until the particle is on the point of taking off from the table. So my force in this direction will have to be equal to my force in this direction for it to just be on the verge of taking off, or however they describe it. So I have my 4t over 5 will have to be equal to my 98. So t will be 5 times 98 divided by 4. So the new tension in the string, it's speeding up, will be 122.5. So that's my new tension. We want to show that the angular velocity, okay, so going to the right hand side, I'm going to get 3t over 5, so 3 over 5 by my new t, which is 122.5, will be equal to m by w squared by the radius, which is still 0.3. So we have a cancellation, we've got my 3, so w squared this time will be equal to 122.5 divided by 5, which is 24.5. So the new angular velocity will be equal to the square root of that, 24.5. And actually that's just what we're asked to show. Show it's equal to the square root of 24.5 radians every second. Question 9. We have a particle P of mass 4 on a smooth horizontal table. It's connected by a light inextensible string which passes through a small hole in the table to a particle Q of mass 2.5. Okay, let me try this diagram. It's on a table and it's connected by a string to a hole in the table where the string goes through the hole and is connected to a new particle Q. And P is going to have this circular motion still going around. Not bad for freehand circle drawing. Okay, so what mass is P? P is 4, so 4g. It's on the table, so there will be a reaction at the table. And we have tension in the string, which is connected to Q as well. And the Q mass is 2.5 kilograms, so 2.5 g going down in that direction. P describes a circle of radius 0.5. Okay, so 0.5 here for my radius. And Q is kept freely hanging, so it's in equilibrium. So if it's kept freely hanging, it's not moving, so the opposing forces have to be equal. And it's at a height above the floor greater than 0.5. Okay, find the angular speed of P. There's a lot going on here. So what we start with here, we will start, well, if it's Q is in equilibrium, the tension in the string, it's not moving down Q, so 2.5 G will have to be equal to the tension in the string. So tension 2.5, 9.8 is 24.5. 24.5 newtons is the tension in the string. Then we have, let's see what's next. We need our forces. So no triangles. On this direction we have our tension, and that's going to be equal to the centripetal force or angular speed, so mw squared r. So we have tension is 24.5. We have the mass is 4. We're looking for angular speed, and we have the radius is 0.5. So that's 2w squared on the right, so 24.5 over 2 will be w squared. So w squared is equal to 12.25. That works out evenly. That's 3.5 squared. So w is equal to 3.5 radians every second for the angular speed. Then P is stopped, held, and released. Show that the acceleration of P is 49 over 13 meters per second squared, and show its speed on reaching the hole, so it's going to go towards the hole, is speed is 7 over root 13. Okay, so what's going on here? T, if we look at my forces, P with forces, it's going towards the hole, so it's going, tension is starting first. There's nothing holding it back, so there's no like minus anything. We'll just say 0 maybe, is equal to MA, which is 4A. And then for Q, Q is going down, so the direction downwards is is 2.5 G. T is behind it, 2.5 G minus T will be equal to MA, 2.58. This will help me solve for the acceleration. 6.5A is equal to 2.5 G. So multiplying by 10, I'll get 25 G over 65 is equal to A, which is equal to 5 G over 13. Is that what they're looking for? No, 49 over 30. Okay, no G, so that's equal to 59.8, which is the 49 over 13 meters per second squared. And then the speed as it reached the hole, so we have its acceleration. So speed, we want V. It was stopped, so the starting speed is 0. It has to travel a distance of 0.5, and its acceleration is 49 over 13. V squared is equal to U squared plus 2AS. We're looking for velocity, looking for velocity. U squared is 0, so 2 by A by S. I'll do the 0.5. 2 by S by A. So the 2 and the 0.5 just gives me 1, so V squared is 49 over 13. So V is equal to the square root of that, square root of 49 over square root of 13, so it's going to be 7 over root 13. What were they looking for? They were looking for 7 over root 13. Happy days. And that's meters per second. And that's question 9.